Hello, everyone. Thanks again for joining us. This is Applied Force. In this section, we're going to be going over lab number three, which is Newton's second law that has to do with acceleration and the theoretical comparison. Today, we have team members Diego Beltran, Jacobo Nava, Julian Duran, John De Santiago, Yara Velarde, and Samantha Armenta. Hello, everybody. This is John here. So, I'm going to basically talk about the purpose and the theory, and also what the objective is during this lab. So the goal of the experiment was to verify Newton's second law. The way we did this was by comparing a theoretical and experimental data of acceleration on a glider system, which is basically a frictionless air track that Julian will go over and he will describe in the next portion. We also used a capstone software that tracks and collects the data for us as we measure it, and we will show in the graphs later on during the presentation. And it just basically is going to give us the three different ways and how to analyze closely each theoretical value using an equation, which is A equals MWG over MW plus MC. With MW is going to be the hanging mass, MC is the glider mass, G is going to equal to the gravitational pull, which is 9.8 meters per second squared, and which is basically just a direction, using a direction forward sensor that basically sends sound waves that will track the movement and then give us back the data.
Hello, this is Julian, and in this slide, I'm going to be talking about the equipment we use for this lab. So the first thing we used was the air track and the glider. The air track is just like an air hockey table that has tiny little holes that shoots air through it, just to simulate a frictionless surface. And the glider is, of course, like the hockey puck um, that will glide back and forth on the track. We also use a motion sensor. Um, it basically just sends waves to sense exactly like where an object is, and it stops whenever it hits an object, and it sends it back, and it just gives us the position, of course, and that's how we get our position graph, and that's used with the capstone software. We also use a pulley system with a string and a small hanging mass, as you could see in the second picture right there on the top right. Um, that was just what we used to actually have the glider actually go back and forth. And we also used a leveling tool to ensure that the track was level and make sure that everything was exact and how we wanted it to be. And we also used a scale, and that we actually weighed um the glider and the string. We didn't weigh the weights though. So everything else was separate, and the scale was only used for the glider.
Hello, this is Yara. For this experiment, we set up a nearly frictionless air track to reduce surface resistance while the glider was moving. The glider was connected to a small hanging mass using a lightweight string that passed over a low friction pulley. This setup provided a net acceleration force needed to move the glider. The motion sensor was placed at one end of the track to record the glider's motion towards it. Using Capstone software, we recorded real-time data for position, velocity, and acceleration. Before each run, we made sure the track was leveled and zeroed properly to ensure our data was accurate. Once released, the hanging mass accelerated downwards, pulling the glider smoothly towards the motion sensor. The software displayed motion graphs immediately showing the relationships between position and time, velocity and time, and acceleration and time. We performed multiple trials and averaged the data to minimize random error and improve consistency. Finally, we assumed friction and air resistance were negligible, though we discuss small effects of these forces later in our analysis. Thank you.
So right here is a video of us actually doing the experiment. So in the procedure, I had to just have the glider at a certain point on the track and just let it go and let it bounce off of the rubber band and just let it bounce back and forth so we could actually simulate that graph that you see in the bottom right. It goes down, bounces up, and it all goes up and down. Exactly the same every time, just lower and lower as it starts to lose um, its speed, and of course starts to go all the way down till it hits zero. And this is just the top graph is the position, of course, and that's just a more zoomed in extended version.
Hello, my name is Jacobo, and today I'll be explaining the calculations that we use to find the acceleration of our graph. We first started off by finding the theoretical acceleration using the mass of the hanging object, labeled mw, and the mass of the slider, labeled mc. along with the acceleration of gravity, which was labeled as g. Using the equation, the theoretical acceleration equals the mass of the object times gravity over mass of the object plus the mass of the slider. We then added 10 grams of mass to the hanging mass, making it a total mass of 15 grams, which we convert to 0.015 kilograms. And the mass of our slider is 196 grams, which we later converted to 0.196 kilograms. And gravity is, of course, 9.8 meters per second squared, but we'll be using it as a negative. Now, to get to the real calculations, we plug in all of our variables into it, which will be the theoretical acceleration equals 0.015 times negative 9.8 over 0.015 plus 0.196 equals negative 0.6967 meters per second squared. We then calculated the acceleration using a position time graph. To do this, we got 4 points from the graph. Point 1 was at 4.4840 seconds and 0.45 meters. Point 2 was located at 4.885 seconds and 0.44 meters. Point 3 at 5.331 seconds and 0.34 meters. And finally, point 4 was at 5.400 seconds and 0.31 meters. With these 4 points, we used them to calculate the initial velocity between point 1 and 2, and the final velocity between the points 3 and 4, using the equation velocity equals final position minus initial position over final time minus initial time. With this equation, we plug in the values as initial velocity equals 0.44 minus 0.45 over 4.885 minus 4.840, which equals to negative 0.2222 meters per second for the initial velocity. For the final velocity, we did final velocity equals 0.31 minus 0.34 over 5.400 minus 5.331, which equals to negative 0.4348 meters per second. After we found both the initial and final velocity, we can finally find the acceleration using the equation acceleration equals final velocity minus initial velocity over the change of time. To do this, we first find the change of time using t equals 5.400 minus 4.840, which equals to 0.560. With that, we plug in all of our variables, which will be acceleration equals negative 4.348 plus 0.2222 over 0.560, which equals to negative 0.3796 meters per second squared. After that, we calculated the acceleration using a velocity time graph. To do this, we got 2 points from the graph, point 1 being 4.840 seconds and negative 0.070 meters per second, and point 2 being 5.4 seconds and negative 0.410 meters per second. With these points, we use the equation acceleration equals change of velocity over change of time. To find the change of velocity, we do negative 0.410 plus 0.070, which equals to negative 0.340 meters per second. And for the change of time, we do 5.4 minus 4.840 equals 0.560 seconds. So with these variables, we plug them into the equation to find the acceleration, that being acceleration equals negative 0.340 over 0.560, which equals to negative 0.6071 meters per second squared. Then we used Capstone to calculate the mean value of the acceleration time graph, which ended up being negative 0.670 meters per second squared.
This slide just shows the calculated percent error for our experiment. The formula we used was the absolute value of the theoretical value minus the experimental value, all divided by the theoretical value, then multiplied by 100. Using that equation, we calculated the percent error for each of our 3 accelerations. For position versus time graph, the error was 45.5%. For the velocity versus time graph, it was 12.9%. And for the acceleration versus time graph, the percent error was 3.83%. Overall, the error decreased with each method, showing that our results became more accurate and consistent as we analyzed the data in different ways.
Hello, my name is Samantha Armenta, and for I'm presenting analysis and discussion. Percent errors were not identical but decreased from acceleration 1 to acceleration 3. More direct methods produce more accurate results. Errors came from pulley friction, string tension, air resistance, and rounding. In capstan, percent errors can never be exactly zero due to small systematic and random errors. Quality thresholds good was less than or equal to 10%. Regular was 10 to 25%. Bad was greater than or equal to 25%. Best method, acceleration time, friction and air resistance are negligible is partly true, small but not zero effects. A variable can be considered negligible when its influence on results is insignificant compared to main forces. I will be doing the conclusion as well. Therefore, theoretical acceleration calculated as negative 0.697 meters per second squared. Experimental accelerations were close to the theoretical value. Acceleration time method gave the most accurate result. Small differences due to minor friction, pulley resistance, and measurement errors confirm Newton's second law. Acceleration is directly proportional to the net force and inversely proportional to total mass. Friction and air resistance considered negligible but not zero. This was a successful and accurate experiment, and we also put here the credits for who did what. So, yeah, thank you.